In this lecture, we will be discussing the statistical properties of incoherent scatter radar signals. As the name of the topic implies, this lecture will primarily be about statistics, but I will try to show connections to the underlying physics as well. While the material I'll be discussing is focused on incoherent scatter radar measurements, the concepts are widely applicable to radio science in general. You will encounter the same concepts in many other types of radar measurements, as well as radio measurements in general. For example, the statistical treatment of signals in radio astronomy shares many of the same concepts that we will introduce in this lecture. Okay, here is a general overview of the topics that we will be covering in this lecture. The figure shows the elementary stages of an incoherent scatter radar measurement. The first step of a measurement is transmission of a powerful radio wave. This is denoted by the incident wave vector, Ki. The radio wave illuminates a volume filled with radar scatterers, which are electrons in the ionospheric plasma. Each electron in this figure is denoted with a black circle, with the position of each scatter as a function of time indicated with the vector Rn. The electrons inside a volume of plasma scatter a small fraction of the transmitted electromagnetic wave. The scattered wave is denoted with the scattered wave vector Ks. The scattered electromagnetic wave, including contributions from all of the electrons inside the volume of plasma, is then received by the radar antenna. The electric field received by the radar antenna is denoted with EFT. In addition to the radar echo from ionospheric plasma, the received signal also includes contributions from other radio sources, primarily of cosmic origin. This includes bright radio stars, our own sun, as well as galactic synchrotron emission. The contributions of the electrons inside the plasma are denoted here in this first part, and then noise sources of cosmic origin are denoted by Xi of sky. A depiction of the electric field at the receiver antenna is shown on the plot in the right. The electric field oscillates very fast due to the frequency of the radar transmission, omega naught. Once the radio wave reaches the antenna, it propagates through a radio receiver, which amplifies the signal and filters a portion of the electromagnetic spectrum where the radio signal of interest resides. During this process, more noise is added to the signal due to losses in the radio receiver components. The primary sources of noise are the first stage preamplifier of the radio receiver and the transmit-receive switch. The radio receiver also performs a frequency shift operation and filtering operation, which is called complex baseband conversion. This is accomplished by multiplying the received signal with a complex exponential, after which the signal is low-pass filtered. This process has the effect of removing the oscillating term omega naught from the signal E. Another consequence of this shifting operation is that the signal becomes complex valued. A plot of the complex voltage V of t is shown on the right-hand side. This signal now no longer oscillates very fast because the down conversion has removed the omega naught term in the signal. The next step of signal processing is estimation of an autocorrelation function from the received complex voltage. While making this measurement, we make the assumption that the second-order statistical properties of the signal do not change as a function of time, while we average over multiple radar pulses to obtain an estimate of the autocorrelation function. An example of an autocorrelation function is shown on the right. The autocorrelation function has a characteristic behavior that shows a gradual decorrelation of the complex voltage as a function of time lag tau. This is because the radar echo from the ionosphere decorrelates as a function of time as the constituents of plasma move around and are reconfigured. The autocorrelation function measurement also contains noise. This is due to two reasons. First of all, our measurement includes additive receiver noise, which is not of ionospheric origin. It consists of cosmic radio noise as well as noise generated by the radar receiver. Additionally, the ionospheric echo itself is a random process. We are not interested in measuring the random realization of this process, but estimating the second-order statistical properties of this random process. So the ionospheric echo in itself is also a source of measurement error when estimating the autocorrelation function. The autocorrelation function is then used to derive ionospheric plasma parameters: electron density, ion temperature, electron temperature, ion velocity are typical parameters. We can also measure ion mass under some conditions. Sometimes we can measure neutral temperature or even neutral wind. The theory for incoherent scatter is a theory that provides us a spectrum provided the plasma parameters. In order for us to relate our measurement of the autocorrelation function to the spectrum, we rely on the Wiener-Khinchin Theorem, which states that the autocorrelation function and the power spectrum of a random process are a Fourier transform pair. We will begin by introducing the complex baseband representation for band-limited signals. This is a very economical representation for radio signals in general, as it only includes the spectral components of the signal of interest, allowing a low bandwidth representation of signals which otherwise have a very large center frequency. Let's start by investigating a cosine signal. This can represent, for example, the electric field of a continuous wave signal measured by a radio antenna. This signal is defined by 3 parameters: the amplitude, E0, the phase, phi, and the angular frequency, omega. The angular frequency can be related to frequency in units of cycles per second or hertz by this relation. The information content of this signal resides mainly in the amplitude and phase. However, the angular frequency can be very large in the case of radio signals. For example, the Svalbard radar has a frequency of 500 MHz. Representing this signal as a rapidly oscillating function is therefore not very practical. We can come up with an alternative representation for the signal with the help of Euler's formula, which is given in equation 3, which splits the cosine function into 2 complex exponential signals, one with a positive frequency and one with a negative frequency. We can then proceed by multiplying with a complex exponential with a negative frequency, e to minus I omega t. This has the effect of shifting the complex exponential signals down in frequency by omega. One of the complex exponentials is now a constant, in other words, centered at 0 frequency, but the negative frequency component now has twice the original frequency. The last step is removal of the high frequency complex exponential components. The remaining spectral component is now a complex constant. However, this complex constant still encodes the amplitude and phase of the original signal. Assuming that we knew what omega is, we can still reconstruct the original signal using this representation. This is the basic idea behind complex downconversion. Let us now derive a general definition for complex baseband signals. We start by representing a real-valued signal x of t with the help of a Fourier transform. Here, x omega is a spectral representation of signal xt. Because our signal is real-valued, we know that the spectrum is conjugate symmetric. This follows from the definition of the Fourier transform. The negative frequency spectral components are conjugated versions of the positive frequency spectral components. This means that only half of the spectrum contains all of the phase and amplitude information of the original signal. Now let us assume that our signal is narrow-band spectrally. What this means is that the spectrum of the signal is zero-valued everywhere else except a narrow range of frequencies, and zero-valued everywhere else. When the signal is narrowband, we can rewrite the inverse Fourier transform representation of x of t using finite limits. So instead of infinite limits, we can express it as 2 finite limits: positive frequencies and the negative frequencies. Now, because our signal is real valued, either one of these integrals will contain all of the information of the signal. In our case, we have selected the positive frequency spectral components, but we could have just as well selected the negative frequency components. The last remaining step is shifting in frequency so that the frequency of omega naught will correspond to 0 frequency. This is achieved by multiplication with e to minus I omega naught times t. And equation 14 now represents the definition of a complex baseband signal. The following diagram shows the different stages of a complex baseband downconversion process in terms of the spectral components of the signal. On the top, we have the spectrum of the original band-limited real-valued signal with positive and negative frequency components confined to within a narrow band of frequencies. The middle plot shows the spectral components after multiplication by e to minus I omega naught t, which shifts all of the spectral components in frequency. Finally, the bottom plot shows the spectrum of the signal after low-pass filtering has been applied to remove the high-frequency components of the signal, which were shifted to around minus 2 times omega naught. The resulting complex baseband signal is now centered around zero frequency, and it is complex valued because the spectral components no longer are conjugate symmetric. Here is an example of a narrowband signal, which consists of two cosine signals with frequencies 101 and 99 Hz. The total bandwidth of this signal as a real valued signal is 202 Hz. A complex baseband representation of the same signal using a center frequency of 100 Hz is shown in equation 16. This signal retains all of the information of the original real valued signal, but now has a bandwidth of only 2 Hz. Here is a plot of the real and complex representations of the signal from the previous example, with the real valued signal shown on the left-hand side and the complex valued signal shown on the right-hand side. Here's another example. Binary phase modulated signals are commonly used as radar transmit codes. Binary phase modulation simply means that the signal alternates between two possible phases, 0 and pi radians, or 0 and 180 degrees. Equations 17 and 18 show the 0 and pi phase signals using a real valued representation. The complex baseband representation of this signal is shown in equations 19 and 20. The 0 phase corresponds to 1, and the pi phase corresponds to -1 as a complex baseband signal. In this case, the complex voltage consists of only real values. This is okay, as real numbers are a subset of complex numbers. Had we chosen, for example, phases pi over 2 and minus pi over 2, we would have obtained plus minus imaginary number as the complex baseband representation. The following plot shows the real and complex baseband representations for a 13-bit binary phase modulated Barker code, which is a commonly used radar transmit code. The complex baseband representation is shown above, and the real valued representation is shown below. From the real valued representation of the signal, it is possible to see that when the complex baseband signal transitions from +1 to -1, the phase of the real valued signal shifts by 180 degrees. The aliasing behavior of complex valued signals is different from that of real valued signals. This is important to keep in mind when digitizing a complex valued signal. It turns out that complex valued discrete time signals are twice as efficient as real valued signals when it comes to the amount of bandwidth that a discrete time signal sampled with a certain sample rate can retain. The aliasing behavior can be demonstrated by investigating the aliasing behavior of a single spectral component of a signal, which is a complex exponential signal shown in equation 22. When we discretize this signal with a certain sample rate, fs, or a sample spacing, ts, we obtain a discrete time signal, which is given in equation 23. The continuous time angular frequency omega is now replaced with a discrete time normalized angular frequency, omega hat, which has units of radians per sample. Aliasing of a discrete time complex exponential signal merely means that there are infinitely many continuous time angular frequencies, which can result in the same discrete time signal after discretization. The aliasing behavior for a single spectral component is shown in the following figure. I have added another parallel axis to the figure, which shows continuous time frequencies in units of Hertz, in addition to normalized angular frequencies in units of radians per sample. Aliasing means that it is impossible to distinguish, using a complex valued discrete time signal, which one of the continuous time frequencies the discrete time signal corresponds to. However, it is possible to come up with a one-to-one mapping between the discrete time signal and the continuous time signal if we can make the assumption that all of the spectral components of the signal are within a certain range of frequencies between f-min and f-max. In other words, the bandwidth of the signal. Therefore, the more general Nyquist sampling criteria for complex valued signals is that the sample rate has to be larger than bandwidth. This is very different from the Nyquist sampling criteria for real valued signals, which states that the sample rate has to be larger than twice the largest frequency component. This means that we can fit twice as much bandwidth into a complex valued discrete time signal than we can into a real valued discrete time signal. Without going into much more detail, aliasing behavior for complex valued signals is easier to understand than the aliasing behavior for real valued signals, which always have conjugate symmetric spectral components. Now that we have introduced complex voltage signals, we'll use them to develop a simplified model for volume filling incoherent scatter. This is not a complete model of incoherent scatter from ionospheric plasma. For this, we would need to include the effects of collective interactions between the different constituents of plasma. However, this simple model will hopefully help build intuition on the statistical properties of a radar echo. We will derive our model by assuming that we have a volume of space which is filled with n scatterers. In the case of ionospheric plasma, the scatterers are electrons. We'll then assume that the signal transmitted from the radar propagates as a plane wave to an individual scatterer and continues from there as a plane wave to the radar receiver. The phase progression as a function of distance for each individual path will be given by equation 27. Here k is the wave number and x is a one-dimensional distance. The following figure shows the derivation for our toy model of incoherent scatter. In this case, we have a transmit antenna and a receiver antenna with their positions indicated by vectors ptx and prx. Our model also includes electrons within a volume in space. The position of each electron is indicated with vector Rn. Because the scatterers move as a function of time, this position vector is time dependent. When the radar transmits a radar pulse, the electromagnetic wave propagates from the transmitter to an electron. This is indicated with the incident wave vector Ki. After this, the scattered electromagnetic wave propagates from the electron to the receiver. This is indicated with the wave vector Ks. By adding up the contributions of scattering of all electrons within the volume, we get an expression for complex voltage, which is shown in equation 28. In order to simplify equation 28, we can use the incident and scattered wave vectors to arrive at equation 29. Finally, we can move the common and time constant terms outside of the sum and arrive at equation 30. This constant term only depends on the locations of the transmit and receive antennas, as well as the incident and scattered wave vectors. This is just a complex constant which we can ignore later on when we evaluate the autocorrelation function of the scattered complex voltage. Therefore, we'll ignore this complex constant. Now we have arrived at a relatively simple equation for scattering from a volume-filling incoherent scatter radar target. The wave vector k, in this case, is the Bragg wave vector, which is k incident minus k scattered. Here is a simulation of an incoherent scatter complex voltage radar echo. In this simulation, I have placed electrons inside a volume at random initial positions. I have randomized the velocity vectors using a Maxwellian distribution. The Maxwellian distribution in this case corresponds to a normal distribution. The complex voltage, including the sum of all scattering contributions, is shown on the plot in the lower right. The blue line indicates the real component and the red line indicates the imaginary component of the scattered voltage. On the lower left, I have plotted the same complex voltage on the complex plane. It is easy to see that the mean value of the scattered signal is 0, and the phase of the signal is uniformly distributed between 0 and 2 pi. Here is a real example of what the complex voltage scattered from ionospheric plasma looks like. The two plots show scattered complex voltage measured during two different radar pulses. The blue line indicates the real and the green line indicates the imaginary component of the signal. While this signal is random, it is still somewhat smooth. This is because of temporal correlations within the scattered signal. However, after several hundred microseconds, the complex voltage is already somewhat uncorrelated. This is because the individual scatters within the volume of ionospheric plasma have moved sufficiently for the radar echo to decorrelate. While this example shows the actual realization of the random process of incoherent scatter, It normally cannot be measured as the signal is too weak. There is only one radar in the world that is powerful enough to make this type of a measurement. It is the Arecibo Observatory 430 MHz Incoherent Scatter radar, which has a 305 meter diameter radar antenna. The radar echo given by V of t can be considered as a random process because we can treat the individual positions of scatters as random quantities. The central limit theorem of statistics tells us that the statistical distribution of a sum of a large number of random variables approaches a normal distribution. In our case, we are summing over the scattering contributions of all of the electrons within a volume of plasma, so n can be extremely large. So how large is n in practice? There are between 10 to 8 and 10 to 12 electrons per cubic meter in ionospheric plasma, and the scattering volume can often be several hundred cubic kilometers in size. To first order, electrons that are separated by more than the dBi radius have statistically independent trajectories. The dBi radius within the ionosphere is typically measured in centimeters. We can therefore safely assume that we can treat V of t, the scattered voltage from ionospheric plasma, as a normal random variable. In order to analyze radar signals statistically, we will need to use multivariate or multidimensional normal random variables. Such random variables are characterized using the probability density function shown in equation 32. The probability density function is completely characterized by the mean value of the random variable mu and the covariance matrix sigma. The covariance matrix sigma describes the mutual correlations between the different elements of the vector-valued random variable x. The angle brackets in this notation denote a statistical expectation of a random variable. Let us now define scattered complex voltage as a multivariate normal random variable. Because we are interested in estimating the autocorrelation function of scattered complex voltage, we'll need 4 random variables for the real and imaginary components of complex voltage measured at 2 times t and t plus tau. We will denote these random variables using x1, x2, x3, and x4. These are real valued normal random variables. We then stack these random variables into a column vector x. And the distribution can be represented as a 4-dimensional multivariate Gaussian distribution, shown in equation 35. In the case of radar signals, the mean value of x is 0. This is because the phase of the signal is a uniform distributed random variable between 0 and 2 pi. The reason for this is that the scattering volume is very large compared to the inverse of the Bragg wave number. The covariance matrix sigma is the only quantity that we will need to characterize the joint distribution of complex voltage measured at 2 different instances of time. Each element of the covariance matrix is given by the expected value of xi times xj. Several elements of the covariance matrix sigma are 0 valued, namely sigma 1, 2, 2, 1, 3, 4, and 4, 3. This is because the phase phi of each scattering contribution within Vt, the complex voltage, has a uniformly distributed phase between 0 and 2 pi. This is because the dimensions of the scattering volume are large, which results in k dot Rn being a very large number, and because of the cyclic nature of the exponential function, we can treat this as a uniformly distributed random variable. We can easily see that even for a single scatter, the expected value of the real and imaginary component of the complex voltage multiplied with one another is 0 mean. We'll only need to assume that the distribution of phase is uniform. We then evaluate the expected value of a function x1 times x2 and obtain 0. In a similar way, we can also see that the diagonal elements of the joint distribution sigma all have the same non-zero value. This again follows from the uniformly distributed phase of a single scatterer. Here I've evaluated the statistical expectation for x1 multiplied with x1 and x2 multiplied with x2. and they both have the same value of half. A similar derivation can be made for the diagonal elements sigma 3, 3 and sigma 4, 4. The remaining 8 non-diagonal elements of the joint distribution are terms that contain information about temporal correlations within the scattered signal. For small enough values of tau, these elements are non-zero. This is due to physics. For small enough values of tau, the electrons have not moved much, which causes the echo to correlate. If we inspect the contribution of a single scatter, Vn of t, shown in equation 45, we can see that for small values of tau, the term Rn t minus Rn t plus tau can be very small. In the extreme case, when tau equals 0, the electron has not moved at all, and equation 45 evaluates to unity. However, for a large enough value of tau, the scatter will have moved a significant distance, and once again we can treat k dot Rn t minus Rn t plus tau as a uniformly distributed random phase. And in this case, the cross correlation of the scattered voltage for a single scatter becomes 0 when tau is large. The primary quantity of interest when making an incoherent scatter radar measurement is the autocorrelation function of the scattered complex voltage, R of tau. The definition of the autocorrelation function is given in equation 46. It's the expected value of complex voltage measured at time t multiplied with the conjugate of complex voltage measured at time t plus tau. The autocorrelation function tells us how the plasma reconfigures itself as a function of time, which again depends on the plasma parameters of the volume that is being measured. We can express the autocorrelation function using signal power S and the normalized autocorrelation function rho of tau. The normalized autocorrelation function is a complex valued function which can be expressed using the real and imaginary components. When expressing the complex voltage using random variables x1 to x4, we can see that the autocorrelation function depends on the elements of the joint distribution, sigma. The full joint distribution sigma for two complex voltages at times t and t plus tau is given in equation 51. This covariance matrix is a symmetric matrix. The diagonal elements of this covariance matrix provide us information about signal power, and the 8 non-diagonal elements provide us information about the autocorrelation function of the scattered complex voltage. Using the joint distribution sigma, we can now evaluate the expected value of many different combinations of complex voltage. For example, V of t conjugated times V of t plus tau, which evaluates to a conjugate of the autocorrelation function. And all we need to do to arrive at this result is to express the complex voltage using random variables between x1 and x4, divide them up into two combinations, and then read off these values from the covariance matrix. One case, which is needed later on when deriving the errors of an autocorrelation function estimate, is shown in equation 56. This contains the expected value of voltage V of t multiplied with an unconjugated version of V of t. So this is just V of t squared, the expected value of V of t squared. Now perhaps a somewhat non-intuitive result is that this actually evaluates to 0. Similarly, if we multiply a conjugated version of the complex voltage with a conjugated version of a complex voltage, this is also 0 mean. An important theorem that we will need later when evaluating the errors of an autocorrelation function estimate is the theorem of Isserlis. This theorem provides a formula for expressing higher order moments of random variables using second moments of the same random variables. The Isserlis formula for fourth moments is shown in equation 58. For example, using this formula, we can evaluate the expected value of the magnitude of Vt squared times the magnitude of Vt plus tau squared, which is a four product. If we express V of t as V1 and V of t plus tau as V2, we get a 4 product because V1 squared is the same thing as V1 times V1 conjugated. And using Isserlis' formula, we can express this 4 product as 2 products, and each one of these 2 products we can figure out using the joint distribution sigma. And we can obtain this result. When making measurements of the autocorrelation function of the scattered complex voltage V of t, we rely on time stationarity of the joint distribution. This is because the only way that we can make multiple independent measurements of complex voltage is by sending out multiple radar pulses as a function of time and averaging the lag product V of t times conjugate of V of t plus tau. This assumption of time stationarity is known in statistics as the ergodic assumption. A random process which has a joint distribution that is independent of time is called a wide-sense stationary random process. The assumption of ergodicity is given in equation 65, which essentially states that the autocorrelation function does not depend on time. The joint distribution sigma, which we are estimating by using time averaging, however, depends on plasma parameters. And we know that plasma parameters do change as a function of time. The quiet time F region plasma parameters can be assumed to be somewhat constant for over a minute or so, but not much longer than that. One extreme case is auroral precipitation. We know that during active auroral events, the plasma parameters can change already in a fraction of a second. When making measurements of auroral plasma parameters using incoherent scatter radar, one should always use caution, as there is a good chance that we are violating this assumption of stationarity, as the plasma parameters may change significantly during the time period that we are estimating the autocorrelation function. In this case, the resulting autocorrelation function estimate will not be a true representation of the plasma parameters that we measure. The Wiener-Khinchin Theorem allows us to relate the measurement of the autocorrelation function of the incoherent scatter radar echo to a power spectrum of the same quantity. It is important because the theory for incoherent scatter radar provides us a spectrum, while our measurements provide us an autocorrelation function. The Wiener-Khinchin Theorem states that the autocorrelation function and the power spectrum of a wide-sense stationary random process are Fourier transform pairs. Here is an example of the Fourier duality of the power spectrum S omega and the autocorrelation function R of tau. On the left-hand side, you can see an incoherent scatter spectrum S omega corresponding to typical F region ionospheric plasma parameters. I've used a non-zero ion velocity. On the right-hand side, you can see the inverse Fourier transform of the power spectrum S omega, which corresponds to the autocorrelation function R of tau. Here is a short proof of the Wiener-Khinchin theorem. We start by expressing the scattered complex voltage random process using an inverse Fourier transform. We also express the time-lagged and conjugated complex voltage using an inverse Fourier transform. We then apply time averaging for the lag product of the complex voltage. This follows from the assumption of wide-sense stationarity, which allows us to evaluate the statistical expectation as a time average. We then insert the inverse Fourier transform representations of complex voltage into this equation. We move terms around a little bit to obtain this line here. And here we can see there's a term here which is e to I omega minus omega prime t. Now, if we combine this integral operator over time with this complex exponential, we can convert this into a Dirac delta. Now when we integrate over d omega prime, we are essentially selecting the values where omega equals omega prime. And in this case, because we're dealing with an infinitely narrow spectral component, we can equate this random variable to the statistical expectation of that random variable, because there literally is only one unique value over infinitely long time for this spectral component. And That essentially completes the proof. The Wiener-Khinchin Theorem now allows us to explore the relationship between the power spectrum of a random process and the autocorrelation function of the same random process using Fourier transforms. One of the properties that we can explore is the relationship of the autocorrelation function and the width of the power spectrum. We will show that the width of the power spectrum is inversely proportional to the width of the autocorrelation function. One somewhat easy function to use to show this is the Gaussian density function, which is shown in equation 70. This Gaussian density function has a width parameter sigma f. If we now apply the Wiener-Khinchin theorem and inverse Fourier transform the power spectrum, we obtain an expression for the autocorrelation function that corresponds to a Gaussian power spectrum. This also happens to be Gaussian. The width parameter of the autocorrelation function sigma tau is inversely proportional to the width parameter of the spectrum. This Fourier transform relationship can now be used to estimate approximately how fast the autocorrelation function decorrelates. For example, the spectral width of the F region ion line, when measured using an incoherent scatter radar, is approximately 1 kHz. Using our result, we can now say that the decorrelation timescale for the autocorrelation function is less than a millisecond. Estimating the power of the received echo from ionospheric plasma is one of the fundamental measurements that can be made using an incoherent scatter radar. The scattered power is a function of electron density, electron temperature, and ion temperature. The complex voltage that we measure using our radar receiver is proportional to the received electric field, and therefore the power of the complex voltage that we receive is proportional to the received sigma power. A measurement of the complex voltage magnitude squared, or the power of the complex voltage, is thus a measurement of electron density, electron temperature, and ion temperature. Often the assumption is made that the electron temperature equals ion temperature. This assumption leads us to a measurement of so-called raw electron density. This estimate is usually an overestimate of the true electron density because the electron temperature is usually higher than the ion temperature. However, a measurement of power already provides a first-order approximation of ionospheric electron density. The constant gamma depends on a number of factors, for example, radar transmit power, distance to the volume of plasma, antenna size, and a scaling constant that relates complex voltage to the received electric field. This constant gamma is often referred to as the magic constant. When estimating signal power, we need to average the magnitude squared of the received complex voltage. This can be done using a sample average power estimator, which is shown in equation 77. In this case, we're taking k independent samples of the received complex voltage that contains an ionospheric echo from the volume of plasma that we are measuring. We'll first investigate how this estimator behaves when there is no receiver noise present, and we can attribute all of the received complex voltage to the radar echo from ionospheric plasma. It is relatively easy to show that our sample average power estimator is unbiased, and it measures the true signal power of the received radar echo. The most important piece of information about our estimator is estimation error. This determines the magnitude of the error of our estimate of scattered power. In order to determine what our estimation error is, we need to evaluate the variance of our estimator, which in itself is a random variable denoted with s hat. The true mean of the estimator is denoted with s. We apply the statistical formula for variance of a random variable using our sample average power estimator as the random variable. This is shown in equation 79. We can then insert the equation that describes our power estimator, which results in a product of two sums. We can divide the terms that result from the product of two sums into two distinct cases. There are k terms where I equals j, and k times k minus 1 terms where I is not equal to j. Both of these cases result in a fourth moment of complex voltage. In order to determine what these fourth moments are, we need to use the Isserlis formula for fourth moments, which we discussed earlier. The Isserlis formula allows us to reduce the fourth moments into second moments, and the second moments can be determined using a joint distribution of random variables. Finally, we arrive at equation 84, which provides us the variance of our power estimator, which says that the estimation error variance is power squared over k, where k is the number of measurements. The square root of the variance is standard deviation, which is signal power divided by square root of k. We can also derive a normalized error standard deviation, which is normalized by true signal power. This is a familiar result from statistics. In other words, our errors reduce inversely proportionally to the square root of the number of measurements. One important note to make here is that we assume no receiver noise. Even when there is no additive noise, our estimator has errors. This is because we're estimating the variance of the radar echo, which in itself is a random process. Here's an example of how we can apply our result. Using the formula for normalized errors, we can estimate how many independent measurements of scattered complex voltage is needed in order to reduce our measurement uncertainty to a certain level. For example, in order to reduce our measurement uncertainty to 1%, we need to average 10,000 independent measurements of complex voltage. This is a very large number, even for a radar that can send hundreds of radar pulses per second. Therefore, the measurement uncertainty for scattered signal power, and therefore electron density, is typically larger than 1% when measuring inline power. Let us now investigate a more realistic situation where we have additive receiver noise. Most incoherent scatter radars operate in a low signal-to-noise ratio environment, where the power of the radar echo rarely exceeds the power of the received noise. In this case, our measurement is the sum of two random variables: the complex voltage, V of t, which represents the radar echo from ionospheric plasma, and psi of t, which is a complex normal random variable that represents the receiver noise. We can make the assumption that the receiver noise is uncorrelated with the ionospheric echo. We'll also assume that the power of the receiver noise is n. Here is an example of what the two random processes look like. On the left, you can see a plot of V of t, the ionospheric echo, which has temporal correlations. On the right-hand side, you can see a plot of the receiver noise process, psi, which has very little temporal correlations and looks like white noise. In order for us to estimate the ionospheric echo signal power from this type of a measurement, we actually need to make two different measurements. One of the receiver noise power, which can be obtained when there are no ionospheric echoes present, and another measurement when we have receiver noise and ionospheric echoes. The estimator for receiver noise is given in equation 90, which assumes that there are kn measurements of receiver noise power. This can be shown to be an unbiased estimator. The variance of this estimator is n squared over kn, which can be obtained in the same way as we obtained the variance for the ionospheric echo power estimator in the previous section. After making an estimate of receiver noise power, we make another estimate which includes receiver noise and ionospheric echoes. In this case, we have KSN measurements. This estimator can be shown to have a variance of signal plus noise squared over KSN. It can be shown that the mean of this estimator is signal noise power plus receiver noise power. Now, in order to estimate the power of the ionospheric echo, we subtract our estimate of receiver noise power from our estimate of receiver noise power plus ionospheric echo power. This estimate is unbiased. The variance of this estimator is shown in equation 93. It contains error variance contributions from both estimators. In most cases, we can make more measurements of receiver noise power than we can make of ionospheric echoes. So typically, Kn is much larger than Ksn. In this case, the variance of our estimator reduces to equation 93. And the normalized error standard deviation in this case is given by equation 95. We can now use our result to investigate what the measurement uncertainty is in this more realistic case where we have receiver noise. Assuming that we have a signal-to-noise ratio of 1, which is typical for F-region ionosphere, we have to make 40,000 measurements in order to obtain 1% uncertainty in our measurement of signal power, and therefore measurement of electron density. We'll now investigate the estimation of the autocorrelation function, which will provide us information of all the plasma parameters, as it is a Fourier transform pair of the incoherent scatter spectrum, as stated by the Wiener-Khinchin Theorem. The formal definition for the autocorrelation function is given in equation 98. We can directly use this formula to come up with an estimator for the autocorrelation function, which performs a sample average of lagged products of complex voltage, which is shown in equation 99. This estimator assumes that the scattered signal is a wide-sense stationary random process, in other words, that the plasma parameters do not change while we are performing this average. In this case, we have k independent measurements of these lagged products. We'll first investigate the case where we have no receiver noise. In this case, it is easy to see that the estimator is unbiased. The variance of this estimator can be derived in pretty much the same way as the variance of the power estimator, so I won't go through this in much detail. When estimating the autocorrelation function in the presence of receiver noise, we again first have to make an estimate of the autocorrelation function of the received complex voltage without the presence of ionospheric echoes, which we then subtract from our estimate of the autocorrelation function in the presence of receiver noise and ionospheric echoes. This estimator can be shown to be unbiased, and it estimates the true autocorrelation function of ionospheric plasma. We can also derive the variance of this estimator, which is given in equation 104. The derivation of this variance is nearly identical to the derivation of the variance for the power estimator we have already discussed. The variance of an autocorrelation function estimate is 1 over k times signal power plus noise power squared, where k is the number of independent measurements of the autocorrelation function that we make. It's now time to summarize the topics that we've covered during this lecture. First of all, complex voltage is a very useful representation for radio signals which are band limited but reside at a very large center frequency. Complex voltage allows us to represent these signals in a very economical way with very low bandwidth. Second, radar echoes from ionospheric plasma, or pretty much any volume filling target in general, can be modeled as normal random variables. These random variables are completely characterized by a joint distribution. For any two complex voltage measurements of the radar echo obtained at two different times t and t plus tau, the full correlation structure is determined by the covariance matrix given in equation 114. When estimating the autocorrelation function of radar echoes from ionospheric plasma, we need to make the time stationarity assumption. This is equivalent to assuming that the covariance matrix does not change as a function of time. This is also an underlying assumption that the ionospheric plasma parameters do not change over the time period during which we estimate the autocorrelation function. The theorem of Isserlis can be used to convert fourth moments of random variables to second moments of the same random variables. This is a useful formula because the second moments are provided by the joint distribution. Evaluation of the fourth moments is required when calculating variances of power and autocorrelation function estimates, which ultimately affect the estimation errors of our plasma parameters. The variance of the autocorrelation function estimator, r hat tau, for the case where we have receiver noise is given in equation 116. The autocorrelation function estimate is what we use to fit ionospheric plasma parameters. Therefore, estimation errors of this autocorrelation function will be reflected as errors in our plasma parameter estimates. Even with an infinitely large signal-to-noise ratio, the autocorrelation function estimator has errors when using a finite number of measurements. Finally, the autocorrelation function r of tau is a Fourier transform pair of the incoherent scatter radar spectrum. The Wiener-Khinchin Theorem states that the autocorrelation function is the inverse Fourier transform of the incoherent scatter spectrum. This is an important result because the theory for incoherent scatter provides us a spectrum as a function of ionospheric plasma parameters. Alright, thank you for listening.